let's move to the next talk. It's Dr. Konishi. The title is Waveform inversion of the broadband body wave data for the 3D ice structure in the lowermost mantle. It's a lesson display. Dr. Konishi. I will give a signal for 5 minutes before
5 minutes?
Yeah. Before the end of your talk.
Okay.
Let's keep time.
Hi, good afternoon, everyone. This is Kensuke Konishi. Sometimes they call me Wesley. Well, I am from University of Tokyo and
connected?
yeah, connected.
And function 7? Function 7. Did you try?
Function correspond.
Yours is function 7, right?
Function set. No, no.
High technology, high risk.
I guess this is not so old one.
That's strange.
Why?
Any questions about the
Don't.
earlier talk? Okay, good. Got it. We need to fully use the time when we important time.
I'm sorry about that. This is Kensuke Konishi, and Bob Gerard is my boss. And I remember he gave a talk about seismic hazard map yesterday. But this talk, I'm going to talk about seismic velocity structure. So, since 2007, we have been studying one-dimensional structure all over the world. But with Kenji Kawai as the central figure, I myself dedicated to developing this waveform inversion for expanding to three-dimensional structure. And this year, we submitted 2 works for Central America and this Western Pacific. So I'm going to talk about this application for Western Pacific. The region we explore is the mantle side near to core mantle boundary. So these are prime region. This boundary is chemical, thermal, and more solid liquid boundary. So it is a very important region in the Earth. That it is essential to know the three-dimensional structure of this. So I've been trying to extend the seismic resolution for more and more fine seismic imaging by extracting the information contained in seismic waveforms traveling in the lowermost mantle. So this is a heterogeneity mapped by Takeuchi in the lowermost mantle. And it is showing the shear velocity anomalies. As you can see, there are two large low shear velocity provinces beneath Africa and the Western Pacific. And in this study, we explore this region because there are good dense seismic network in Japan, and we have many earthquakes around Tonga and Fiji, and the radius between them goes into the Dida prime at this region, and this is located at the edge of large low shear velocity province beneath the Western Pacific. So the fine seismic imaging here can be helpful to understand the origin of this province. So there is a favorable distribution of seismic networks and seismicity around Tonga, Fiji, so there are many works for investigation of this Western Pacific. And these are the seismic approaches for before, but the top four works, actually we also have already conducted waveform inversion in 2009, but these are works for the most two-dimensional structures of this region. And this work by Takeuchi is for three-dimensional tomography, but this is global scale, so it is not for localized structures. So in this study, we use this waveform inversion for investigation to three-dimensional seismic structure of this Western Pacific. This waveform inversion is very easiest concept by making a regular waveform between observed and synthetic. So we can extract full information from full waveform. So the resolution power is high. And by using this equation, we can handle very large data sets systematically and objectively, of course, simultaneously. And we now, based on the formulation by Gara and Hara, so we can compute a population for any elastic and inelastic parameters. So we can ideally determine an anisotropy parameter and an elasticity parameters. Since 2007, as I told you, so we've been investigating this one-dimensional structures, but from this year we started to invert for three-dimensional structures. These are components of our waveform inversion. We have to prepare synthetic waveforms for observed waveforms, and these are computed by direct solution methods. And in order to set up equations, we have to prepare partial derivatives for certain parameters we try to investigate. And we now trying to extract information from lowermost Mantle. So that the seismic waveform may contain many effects from other regions. So we have to eliminate them. So we have to do these static corrections for eliminating other information. And in order to solve inverse problem, we installed conjugate gradient method in this study. And we chose the number of using CG vector by considering acquisition information criteria. And as a confirmation results, we conducted checkable tests to show the resolution power. And I don't think so, but if I have time, I will show you the modified waveforms after showing our result. So this is the dataset we used. So no more than 600 waveforms are inverted. And we collect the dataset from Japanese FNet network. And we chose 35 deep focus and intermediate deep certified events around Tonga and Fiji. And the detailed information for the dataset is here. Sampling rate is 1 Hz, and the pass band we use is 12.5 to 200 seconds. And the average epicentral distances are between 16 to 75 degrees. And we conducted waveform inversion with an initial model plan. This is the unknown parameters we set. We inverted for shear velocity and 18 points horizontally and 8 points vertically. So every 5 degrees in latitude and in longitude, and 8 points every 50 kilometers within the lowermost 400 kilometers. Before showing the result, we show this result of checkable test. We conduct this for showing the resolution power. So these are the input patterns A and B. And if we put these models in turn, every 50 kilometers within the 400 kilometers above the CMB, and the shallower part is fixed to the plane. And these are the obtained models. So even though it is not perfect, but I guess this dataset has enough resolution. So this is the result of inversion. And the depth range above each panel shows how much above the CMB. So this is immediately above CMB, and this is the shallowest part, 400 kilometers above CMB. So we can see two low shear velocity anomalies here immediately above CMB, and 100 kilometers above CMB. We also can see low shear velocity anomaly, and we can see similar patterns in shallower parts than 100 kilometers like this. So in the key points in this slide is these two slow anomalies are separated, and a high velocity anomaly is here between them. And in order to look in detail, I will show cross section. And this is that those two low shear velocity anomalies, and this floating low velocity is this one. So and we can see these anomalies are contiguous, and the shape is tower. So we think these anomalies are tower shaped and surrounded by a bit high velocity anomalies. So this is an interpretation of our model. So these two separated low velocity anomalies immediately above CMB can be explained by small thermal plumes above the CMB. And these tower-shaped anomalies may be showing upwelling flows like this. So this model can suggest that the western edge of the western large ocean velocity province consists of an aggregation of these thermal plumes rather than a single large distinct pile model. How about time? Do I have time? No. So maybe
6 minutes.
6 minutes. So these are one our confirmation of our model. So the variance reduction is around 12%, 20% by using this model, CG5 models. That model was obtained by using 5 CG vectors, and this black line shows ARC for any other model using any other CG vectors. And anyway, we chose this model as the best model. And this is the waveform comparison, and red line is observed waveforms at station K, ZK, and event is here. And the epicentral distances of these seismograms are 68 degrees, and variance reduction is almost 30%. And we can see improvement in this phase. This phase is core reflected shear phase, so called SCS waves. So gray line is for plane model, and blue line is our tower-shaped model. And one more. This is the seismograms for another station and another event. And we can also see improvements here. This is SPS phases. Summary. I couldn't explain much about this. No, I didn't talk at all, but this is actually our second attempt to obtain three-dimensional seismic structure by waveform inversion. So the first attempt was for Central America, but for using larger data set like FNet, we have to improve efficiency in this waveform inversion. So I really concentrated on improving this efficiency of handling. So now we are getting ready for invert any other part of the Earth. And this presentation is about application of this 3D waveform inversion for Western Pacific. It is located at the edge of Western Pacific large shear velocity provinces, and it's applied for large data set. And we obtained fine 3D localized structure that has tower-shaped model, and this is supporting plume cluster model. So thank you very much.
Thank you. Any comments, questions? It's quite an interesting result, but do you have other evidence to support the result? For example, other person model, other person image?
As a what?
他の人のモデル、あなたのモデルの真実はあります。
No, yes, but so yeah, to some extent we obtained robust model.
How about Takeguchi-san's? Takeguchi-san's model for the lowermost mantle.
Yes.
Is it consistent with your result or not? Roughly.
Averagely consistent, but the resolution, the grid density is different.
Okay.
So in the other sort of model, which is that you have dense piles of material, there's still the idea that you have plumes coming from their edges. So I think it's possible to have your plume that you apparently image here coming from the edge of one of these piles. So you can have both. They're not mutually exclusive models.
Do you understand the question?
Was it question?
Professor Taylor, would you like to answer the question?
Yes, I think we're investigating the S velocity, and we get from the three-dimensional velocity model to the physical interpretation in terms of field dynamics is an important challenge. And I think we have a long way to go, and we'd like your help, Paul, and others to link them up.
Thank you very much. I think we have to move to the next talk.